Hey, what's up, everybody?
What's up, people?
Hey, it's just us, JJ,
Terrence.
What did we talk about today? Oh, yeah, go ahead.
So, we talked a little bit about quantum mechanics, many worlds interpretation, inspired by the Sean Carroll podcast with Joe Rogan.
Yeah.
So, you guys should check that one out. It's pretty cool. Me and Juan just talked about, we kind of danced around the whole many worlds thing a little bit in the interpretation of quantum mechanics.
Mm-hmm.
So,
we talked about interpretations. We talked a little bit about in the beginning of like what and like how would you classify yourself as a physicist if you could?
How would you classify yourself as a physicist?
Yeah. How could you?
Okay, I don't remember that.
Yeah, remember? You're like, yeah. Oh, actually, I don't know. We'll see. We'll see if we lost the audio. I don't know if we did.
We had a little hiccup at the beginning.
Yeah, we did.
But we'll fix it.
We'll fix it. But I think if you want to stick around for us sort of talking a little bit about what Sean Carroll had stated in his most recent visit at the Rogan Studios in California, what he has to say about the state of quantum mechanics and the philosophy of it and all that. And it's stuff that we've sort of said before anyway. Yeah.
So it's kind of the graduate student perspective, and we can kind of add a little bit more enlightenment to that whole area. So if you like Joe Rogan, you like Sean Carroll, check out that podcast and then follow up with ours, and it should add a little bit more interesting analysis to that whole thing. So
and leave comments. If you're a physicist, feel free to interact with us. We do answer, we do read the comments and answer them and stuff. So just make sure to share.
Yep.
Like. Subscribe.
Yep. Follow that Twitter.
Follow on Twitter. We're actually trying to engage more on Instagram, but it's an uphill battle for us.
But yeah.
So if you do that, I think that's pretty much it, right?
Yeah, and it's just to make sure you guys remember, it's at Eigenbros on Twitter. Mm-hmm. You can go to our website too. It's eigenbros.com. Yeah. And then we also have the mailing list. You can sign up on there. And we have our Instagram. We're going to try to get some more on there.
For the mailing list, you mail us stuff. We don't mail you.
Mail us presents.
Yeah, mail us presents, money, anything really. Anything that's, actually, nothing tax, anything that's tax deductible for us. We can just say it's for the show. So.
But guys, we even have a TikTok, but we're going to try to see what the hell to do with that. I don't know yet.
I was like,
We'll figure it out.
Yeah. All right.
But
physics memes coming to you.
Indeed. Stay tuned.
All right, stay tuned, guys. 3, 2, 1.
I like that slow dramatic countdown.
It is. I put some new ones in here.
You did some new what?
Some new audio clips.
Ooh.
Yeah. Now it's just a matter of... Damn it. There we go. You ready for this one? Did you hear that one?
I love it. That's like Eric Andre level of applause. Yeah!
It is. I got lucky that I found it a while back. I also got this one just when we were really stinking it up. Okay, enough of that.
Did you pull that from Maury?
Say what?
Did you pull that from Maury?
No.
You are not the father.
No, and then I got, whoa, that one didn't show up. Did you hear that one? Kids, man.
The classic.
Whoa. Okay, the kids can stop.
That's the
all right, everybody. Huh?
That's the one Black Pen, Red Pen uses all the time.
Oh, really? Okay.
Shout out to Black Pen, Red Pen YouTube channel.
Yeah, shout out.
Have you ever seen that channel?
I think I have.
Yeah, he's pretty good.
But I think
Asian dude, Chinese?
I don't know.
Okay.
You would know more than I do.
Yeah, he's math, but he solves problems all the time. Very simple to understand. I mean, they're calculus level, but it's really he really makes it nice and easily understandable.
Yeah. Well, you're more of a YouTube connoisseur than I am, I think.
Yeah, that's my area for sure.
Yeah. Speaking of YouTube, we wanted to discuss a little bit about, it's kind of tradition here in the channel that we talk about some guests that appear, physicists in specific, that appear on Joe Rogan's very influential radio/podcast show.
Mm-hmm.
So here we are.
Yes.
As two graduate students in physics, we kind of
graduate, quote unquote, because I'm no longer a student.
Well, I would say, I like to personally say amateur up and because you're an amateur up until they say you're not an amateur, which is when you get a PhD, right?
I don't like to say amateur. I'm just going to say physicist.
Yeah, I wonder
because we know enough physics to not be amateur. It's just a matter of how much research you do. And also it's like even a non-amateur physicist, they only know their one particular field. So once you have the general amount of knowledge, you're pretty much at the same level as a PhD physicist, which is what we pretty much have.
Oh, I see. Because so your argument is that you're not an amateur in PhD grad school, you get so specialized in something that you're not considered an amateur in that specific thing, but you're an amateur in everything else.
Exactly.
And since everybody else is in the same amateur level,
then you're a professional by that definition.
Wait, you're professional. Oh, so since you're all on the same level, you're not an amateur. That's what you're saying.
Yeah. You're all on the same level at a general physics level.
Yeah.
Yeah.
That's fair.
So
I guess that's fair. I guess for me, I'm always like, man, I'm not an actual physicist until you get the PhD. Excuse me.
But I'd say that's kind of you putting that PhD on a pedestal.
Yeah, I guess so.
Of course, I could sound like I'm sour grapes because I don't have the PhD.
Well, no, but it's like, I mean, neither do I. But I you know what I mean? Like it's like, when is it official? But then again, maybe it's like amateur astronomers. Like that's why they call them amateur astronomers. I'm like, well, you're an astronomer because you're going out there and doing the same thing that astronomers do. Period. Right?
Well, amateur astronomers don't necessarily have to have the degree, or they don't have to even have the training, right?
But you're still an astronomer, right?
Well, I think it's a little bit different because I think if you're an amateur astronomer, it's mostly saying that the distinction there means that you do not have access to the particular facilities that an astronomer gets to have.
Oh, I see.
Yeah, like you can't use their giant observatories that can do leading edge astronomy physics.
Okay.
So I think that's a little bit of a different distinction.
Yeah.
Yeah.
Oh, okay. I see. I see.
I think these things can be cut up many different ways. It just depends on how you're talking.
Yeah. Because for me, it's like, but in general physics, you really just need a pen and paper, right?
Yeah.
So you're like, there's really no cutoff. You're pretty much a physicist, like.
Yeah.
Because
you have all the tools.
Yeah, because you studied it. You have a degree that says you are a physicist.
Mm-hmm.
So that's fair.
Yeah.
Yeah.
So I'm calling myself a physicist.
Oh yeah, 100%. Okay, yeah, you're right. You sold me. I'm sold.
Yeah, right. Good.
I'm a physicist. Anyway, speaking of physicists, Sean Carroll, who I ran into like a couple years ago.
No shit.
At a meeting. It was an APS meeting, I think.
Nice.
And,
you shake his hand?
Yeah, but I forgot his name.
So would you say, "Hey, bro"?
No, I was like, "Hey, man." But I had already read. I think I read one of his books. I think it was. Oh God, I'm like blanking on his first book. Maybe I'm confusing him. I think I confused him with Brian Greene. It was the problem.
I can see that.
Not because they look nothing alike, but
there's like a few like 30-year-old
public physicists that are doing. I mean, Brian Greene does like, I think so. He doesn't do astrophysics. I think
he does string theory.
Yeah. But there are a few of those guys out there speaking publicly like that, and I may have confused him at that moment. So I was like, but I knew who he was.
Yeah.
And I was like, oh wow, this is and I blanked on his name. It's like I was like, hey, I'm a huge fan because like I had seen some of like him in parts of him doing interviews. I think at that point he was kind of like doing like Joe Rogan. Did
he do Joe Rogan back then?
I think so, because Rogan started. Everybody who's been listening to Rogan for since he started. He started with comedians doing like, what was it? He was doing commercials for like sex toys and stuff. You know what I mean?
Yeah.
Having his comedian friends on, like super vulgar stuff. Then he conspiracy level, like very low level, low brow.
Well, he was in it hard in conspiracy.
It was very low level, low brow kind of stuff.
Yeah.
And then, but it was, to me, it was entertaining at the time because it was just like, oh, these are just like knuckleheads, like trying to figure it out. And then he started having like actual scientists on. Right. And I think Sean Carroll at the time, he was a public figure, and so I guess he had him on. But that's probably one of the places that I was familiar with him with.
That's definitely the first time I saw him.
Yeah?
Yeah, Sean Carroll. Because back then, too, Sean Carroll, at least in my sphere of seeing physicists, he was not as big as like Brian Cox or Brian Greene even like Michio Kaku or anybody. You know, so I came on to him late. But then when I saw him on Joe Rogan, I was like, oh, man, I really like this guy. He actually is very understandable.
Yeah, and I don't know if that has to do with like him being an American physicist.
Yeah, he kind of flew under the radar. I guess that was probably that might have been what gave him so much influence.
Probably,
because I'm pretty sure, I'm not 100%, but I think he started his Mindscapes podcast after doing the Joe Rogan show.
Makes
so I think
sense.
his popularity got so much where people started demanding him to do it.
And he has a great podcast. He has like really. Have you had the chance to listen to a couple episodes or no?
I think I've listened to 2.
Yeah, I probably listened to a handful of episodes.
I wish he would get video.
Oh,
I know you're an audio listener,
but
for me, I'm very much a
like
visual and audio. I like both. Okay. I need to have both.
Yeah, I just I would agree with you. For the people that want to watch like him interact with like just like have a sort of table discussion kind of type dialogue.
Because he had like Leonard Susskind on there. I'm like, I want to see this fucking guy.
That was a great episode.
Yeah,
because they were both kind of hashing it out, and Leonard Susskind is much older than he is.
Yeah, so he knows like all that shit.
And he was kind of shitting on him a little bit, I felt, in some parts. I don't know if you caught that.
I saw it long ago, so I don't remember.
Honestly, but I remember hearing bits of it where it was like, he was kind of like, oh, that's like, that's like a, like, because Sean, I guess, had certain, what would you say? He had certain inclinations for certain theories, and Susskind didn't necessarily believe them. You know what I mean?
Yeah.
Like he's a many worlds, like basically.
He's the proponent for many worlds.
He's a true believer in many worlds. If you're a physicist, there's many names to this too. Everettian, he calls himself, that kind of thing, and I think Susskind was kind of like, I'm not married to these ideas yet.
Yeah. I get the impression from a lot of physicists, though. But that also makes sense because I think Leonard Susskind is more the traditional type of physicist.
Yeah.
And you know how this is one of the things that Sean Carroll talks about is that, physicists don't really like to analyze a lot of times with quantum mechanics, at least, like why it is the way it is.
Yeah.
And because this kind of falls into philosophy territory.
Yeah.
So I imagine Susskind probably doesn't even want to go there because he knows that Copenhagen is the kind of interpretation that we use.
It works.
Yeah. And I think he's probably hesitant to talk about many worlds in some kind of definitive way, unlike Sean Carroll, because I don't think he's really as interested in pursuing the philosophy aspects of quantum mechanics.
Yeah, which made this conversation that he had, we've been having this conversation.
Yeah.
And I guess it's sort of trickling up because like professors like him, I think are starting to see students try to piece a bigger picture together.
Right.
Because before, a lot of physicists, they train a lot of physicists to just shut up and calculate, the von Neumann.
Right. The classic phrase, shut up and calculate.
Yeah.
And I know both of us have been bothered by that.
Oh, hell yeah.
Phrase. And you know what? I was actually thinking about this. This is very much a TI versus TE issue.
Is it?
And going back to MBTI.
Okay.
So I know some of the people who watch us. Just for people who may not be familiar, I'm very much a Myers-Briggs type indicator
connoisseur.
Yeah, like hobbyist connoisseur.
Okay.
And there are 2 dimensions it's a personality typing system. And basically, long story short, you can be a thinker or a feeler. And if you're a thinker, there's 2 subtypes of feelers, which is extroverted thinking and introverted thinking. And basically, to sum it up, an introverted thinker kind of cares about the why a lot of times. And the extroverted thinkers just want to know how it's done, or just want to know how to use it. It's hard to explain. It's like how to
apply it.
Yeah, like how that applies, and like how's this going to be useful in real life.
Yeah.
It's an objective function. Since it's extroverted, objective functions are extroverted, and introspective functions are subjective. So it's kind of like you're concerned about the introspective subject. If you're introspecting, you're concerned about the extroverted outside world.
Sure.
If it's objective. So yeah, I think physics can go both ways, TE and TI, which is extroverted thinking, introverted thinking. But I think predominantly it's going to be an extroverted thinking kind of area. And I think quantum mechanics is steeped in the extroverted thinking era, I want to say right now.
Yeah.
And it's kind of interesting because I've noticed that there's like cycles. I don't really know for sure, but if you think about it, Newton was kind of the extroverted thinking of science. That's how it started. So
would you say extroverted thinking?
Yeah, I would say it was.
How do you develop mathematics to that level? Because you have to ask yourself why a lot of the time.
Yeah.
To build those tools,
maybe
right?
there's a combination of the two.
Yeah.
But I think mostly it's extroverted thinking in the sense that he kind of just took F equals ma as some kind of assumption, and then he kind of let the ball roll by itself by just doing the mathematics and creating the mathematics that kind of showed where it led to. Einstein was the introverted thinker in the sense that once you hit that roadblock, it's kind of like you had to come up with some kind of new framework of analyzing.
Yeah.
And then that was the introverted thinking part. And Einstein, his biggest power was his introverted thinking. So he came and surpassed these boundaries by thinking about these little Gedanken experiments, which kind of took him over the limit.
Yeah.
And I think quantum mechanics is very much an extroverted thinking thing as well, because Schrodinger just invented this equation that somehow worked.
Yeah.
And then he carried it out, and all of these things somehow worked properly.
Yeah.
And I think it very much is an extroverted thinking. It's a very extroverted thinking era, I guess, right now. And I think what's going to break that is perhaps it could be the introverted thinking, which is where Sean Carroll is trying to go, where you have to start now looking at why it happened.
Yeah.
So, of course, everything's a combination. But, yeah.
But you're saying right now it's been dominated. The sort of one side has been over, like if you look at it as scales, right?
Yeah.
The TE scale has the most weight right now.
Yeah. I think it's very much in TE mode right now.
Yeah. I think you may be right. I think at least a lot of the dominant thinking is that way.
Yeah.
Because I think most of the field is inundated with, let's get you up to the technical prowess that we need you to be at in terms of mathematics, so that you can be on the same playing field as everyone else.
Yeah.
But all the actual physics and concepts are you're kind of left to. They don't really spell it out for you.
They really spell it out, or they don't?
They really don't spell it out for you, in the sense that, like, I had to have a whole course at the end of my undergraduate where professors would have like a sort of seminar style class to make sure that we all understood that the physics and we didn't have any kookery going on. You know what I'm saying? I think I mentioned this to you, but
maybe I don't remember.
Like so you don't walk out in the class believing any woo type of thing. Like,
I don't know if they can stop that because it still happens.
No, sure, but you don't have these misconceptions of like particle is both a wave and quantum mechanics is like a particle is both. Well, you have the duality, the particle and the wave kind of thing. They made sure that we understood that there are boundary conditions that make it such that, experimental conditions that make it such that, you see certain behaviors, you see wave behaviors. They try to reiterate to you, like, or reframe it so that it's more cohesive.
Okay.
Because they understand that the whole undergraduate thing is just like you're barreling through courses.
Yeah.
And a lot of the concepts might not stick. So,
well, I think this is also goes back to why Sean Carroll's pursuit is kind of important.
Yeah.
Because I don't think you can really undo all the woo if you don't actually know what the hell is happening.
right.
I think you can kind of always step around it,
yeah.
mathematically, and kind of only make very, very objective claims.
Yeah.
Well, maybe that's the wrong word, but very testable claims.
Yeah. Yeah.
But anything beyond that, you really can't talk that much about. Like, I've had so many misconceptions in quantum mechanics, even after taking 3 semesters worth of quantum. Just because when I've tried to think about it in some intuitive way, all the pop sci things I've watched and all the things that I've tried to look or try to ascribe some interpretation myself wind up being turned on its head.
Yeah.
Because it means I'm either analyzing it wrong or, it just doesn't work like that.
Yeah, because a lot of the pop sci stuff suffers from not using the mathematics.
Yeah.
And like, because if the mathematics tells you one thing, it's hard to relay that to words sometimes, because it's like none of this mathematics is real, right? It's all an abstraction, right?
I don't know if I'd call it not real. I'll hesitate to say that because that's almost a whole nother philosophy debate in itself.
It is.
But it's like, just because the math is doing something, it doesn't necessarily tell you what is actually happening in the system.
That's what I mean.
Yeah.
Yeah.
Like, we can represent, like, for instance, with engineering, you can do things like impedances, which is like another form of resistance. So if you remember circuits back in the day, let's say if you took an intro physics class, there's a wire, copper wire. Wires have current that pass through, and then those wires have a certain resistance, which is basically how much current can pass through that wire. And there's actually even a component in electronics called a resistor. So you can have different resistors which allow different amounts of current to come through. So in engineering, there's these things called impedances that use imaginary numbers to quantify those resistances. So, and it's a real thing, but it's like, to what extent does the mathematics in that match reality? I don't really know, because you're using imaginary numbers, right? But there is information that you can get out of those imaginary numbers,
right?
So it's very hard to talk about what's real and what's not real mathematically. I think
because the analog in quantum mechanics is like almost all of the things that we deal with have a lot of imaginary stuff in them already, and we get rid of those imaginary things by doing specific things like taking the
like the square of the wave function,
exactly, to get rid of them. So is that physical? Does that actually happen when we collapse the wave function? When we measure something, does that us normalizing the wave function? You know what I mean? Like, what is
because
that?
The thing is, you could see, it's like almost like you're peering behind the veil, is like what we say.
Yeah.
You could see all the mathematics behind it, and you see like these imaginary terms and things, and then eventually, in real life, though, when you measure something, you only see the real parts of those measurements.
Yeah.
So you could see all this imaginary crap, and the mathematics all works and it makes sense. But then in real life, you're just getting that real part, and that's all you see. So it's like you really don't know. It's hard to say what's real, but the thing is, that math is necessary for it to work.
Yeah.
If you don't have that stuff, then it doesn't work.
Yeah. So back in the day, funny enough, a lot of physicists were having the same conversations we're having. They were debating extensively, and I think in a little bit of our history of quantum mechanics, or what is quantum mechanics video, kind of details some of this. But Sean Carroll actually brought up some of this, and I don't know if I mentioned the quote in this video that we did, but there was a funny quote by, I think, Einstein and Bohr were debating. They were debating quantum mechanics, and Einstein said, so when you look up, so you're telling me that the moon doesn't exist until I look at it? Is that what you're talking about? Like, he was like, dude, this is absurd. Like, and, but because, like Sean Carroll is saying, he believes the world is, we have infinite branches of, he doesn't say infinite, but practically infinite.
Well, practically infinite, yeah, you're right.
Yeah, sort of uncountable.
Well, he doesn't even make the claim if it's uncountable.
Okay.
He suspects, I think, that it's uncountable, but I don't even know if he made that claim.
Right, very true. Yeah, because it could very well indeed be finite. Because it's like, for me, that was my thing. Like, I'm like, how could you be my problem with many worlds theory is that and I think I relay this all the time, but it's like, where does the universe get all this like energy from? Like, if we consider the energy as the universe as a closed system, right? Like, how do you reconcile the fact that
that's exactly what I was kind of thinking too, why my intuition feels like many worlds is wrong.
Yeah.
But of course, this is one thing to always know about physics. Your intuition can always be wrong.
Right,
Don't ever think that you're right. But my cocky intuition right now is thinking like, really, we got to have a universe for every choice that happens? Like, it seems so energy inefficient.
Exactly.
And it just, to me, from all the patterns I've seen in the universe, it's like the universe likes the simplest, most energy efficient answers, at least.
Yeah.
And to have a new reality every single time. Maybe we should explain a little bit what many worlds is saying. So what happens is basically in many worlds, let's say it's as simple as just like having a choice. So if you have a particle that has two different states, let's say, can we make it even simpler? Let's just say we have a choice A and a choice B. If we choose, let's say, though, that choice A and B gets collapsed or it falls into one choice once we've
interacted with
something, all right?
Yeah.
So let's call the interaction a button. So we push a button and we get either A or B. We don't know which one's going to happen.
Yeah.
So what happens is when we push this button, A comes out. Now, in many worlds, what's happening, it's saying that just because we see A in this timeline or in this universe, you could say, that doesn't mean that that's the only choice that happened. It means that once you push that button, A and B both happen, but once that happens, A splits into a certain universe, the one that we're existing in now, and B splits into a completely different, branch of the universe where you cannot ever exist in that universe again. So once you've made that choice, you now have broken into two different universes. And this happens, an insane number of times.
Yeah, because you can imagine the fractal nature of this, right? It just like spreads out.
And just gets more and more and more.
Practically infinite, in my opinion.
But of course, like, to me, it's like, I can't really rule that out because just the fact of all these patterns in the universe that already exist, who's to say that we're not an infinite thing already? Like, why can't that make sense? It could make sense.
It could, but I'm like you were saying in studying this, and I see the same thing. Why would the universe typically follows a path of least action?
Yeah.
And energy is minimized a lot of the time, and it doesn't make sense. But like we were saying, sense is kind of your own intuitive sense doesn't a lot of the time leads you astray because your sense of scale is
but then here's another thing, Juan. I was thinking also maybe it does make sense because the fact that you're pushing this button, right? It's kind of already saying that it's almost like the universe is deterministic already then.
Yeah.
Because it means that it could be that these branches have already always existed.
Yeah.
But it's the fact that you're just traveling through it in a certain in a certain time. But this has already existed, let's say, now until the end of time. So these branches have already existed, and it's not really energy efficient because they've already existed. It's just all the choices have already been made. It's just that we're just going through the arrow of time.
I see. That's a good rebuttal
in our framework.
That's a good rebuttal because you're saying all the energy has been accounted for.
Yeah.
So that's a good point. That could also be the case. But you would need to make the case that this actually also, I could see another case for many worlds being that this kind of goes against my own inclination, but that you're increasing entropy because,
entropy is supposed to increase.
The disorder of you're kind of increasing the disorder of the universe because it makes more sense for us for things to coalesce into one thing as opposed to...
Well, entropy does increase. It's supposed to increase.
I know, but that's what I'm saying. But my intuition about this whole thing is I imagine events coalescing into one thing. But I'm saying with taking into consideration that in nature things are left, to evolve in time, things naturally are inclined to states of randomness. Right?
I gotta think about this. Things are naturally inclined to states of randomness. You mean things tend to disorders, what you're saying? Okay, so this is the concept of entropy.
Yeah. So it would make more sense in many worlds for it to be a branch as opposed to coalescing.
Well, many worlds is a branch.
Exactly. That's what I'm saying. Like that lends more credence.
Oh, so you're giving more credence to the many worlds. Okay.
That's what I'm saying. I'm kind of like.
Okay, you're arguing now on the same side.
Well, I see that's a point in there,
on the Sean Carroll
side.
On their
board, yeah.
Okay.
Because I'm inclined, my human sort of brain wants everything to coalesce or order into one outcome.
Yeah.
It's simple.
It's easier for us to hold on to.
Yes.
We hate divergent anything, right? We love convergence over divergence.
Yes, I
think naturally that's what most humans would prefer.
Yeah, and that may very well be working against us because I'm inclined to say, well, it coalesces. It should coalesce into one thing, but it might very well not. It might very well be like a branch. It's just like things are branching out because you're increasing the sort of entropy of the universe in a way, or the meta universe. If there are indeed multiple universes like that come out of this.
Yeah.
I'm still hesitant.
Yeah. Of course. I'd like to look into it more though, because this is something that I feel like Sean Carroll said, we just don't really talk that much about. Yeah. And we kind of treat the Copenhagen interpretation as the interpretation.
Well, because it works.
Yeah. Well, because it's like, it's kind of just like the most hands-offy kind of approach we can use to just do what we need to do and then kind of get the fuck out of here.
What's testable in many worlds?
Nothing yet, I don't think. That's the thing. That's the problem.
There are very few mathematicians, I think, like maybe Penrose, I think, is one of the few people that have proposed certain things. Like we should see certain signatures. And there's a great lecture that you guys can check out. And I think you've seen it too. You sent me something about it.
On Penrose?
Yeah, a while back, but this was like probably a year more
Yeah,
ago.
I think I know what you're talking about.
He gave a lecture where he was talking about you can see signatures of universes if or what he proposes, you would see certain things out in space if indeed there are
many
how
worlds?
Would you say? No, not many worlds, but previous iterations of our universe. Like his working theory is that the universe goes on a singular timeline, and we could effectively look back in time and see remnants of our old universe. But I'm saying you could probably use some of this foundation to kind of figure out if there is multiple universes.
That's a little bit tough to me because I'm thinking that with a many worlds interpretation like the Everettian approach, it could be different in the sense that it's not really the same kind of quote unquote universe. It's almost like how we think of in sci-fi with the concept of alternate dimensions.
Oh, they're not spatial.
Yeah, like there's some it could be a perpendicular to our time axis or something.
Okay.
And imagine if we lived in a Hilbert space of time. You know what I'm saying?
Right.
It could be
for people that don't understand, Hilbert spaces
give
are
some clarity there.
Just sort of the classical imagination, or imagining of this is like a hotel with. Have you heard about this? The hotel with. I don't need to get into that. So let's just say this: Hilbert space is like a fancy space where we say that it's practically infinite.
Yeah. So just think of it like this: if you remember in algebra class. We've got the Cartesian coordinate grid. We've got y-axis. We've got x-axis.
Yeah.
In Hilbert space, you have n number of axes, basically. So you could have an n-dimensional space, essentially. So instead of a y and an x, or sometimes a z like you see, you could have a y, x, a, b, c, d, so on and so forth.
Yeah.
And something that you cannot even visualize.
A lot of the time, no.
Yeah. Well, you can, because we can't visualize anything past 3 dimensions.
Well, I know certain mathematicians might be challenged to do this. Well, here's the thing.
I highly doubt anyone could ever imagine this.
So
it's impossible.
The other thing is you can sort of imagine, dang, what would you say? because we deal with them in matrices, and if you know, it's not like the movie Matrix, but it's there are points in space that are assigned coordinates, and this goes back to what Terrence was saying. Like, you can think of like the same coordinates you learned in algebra, but imagine like you're mapping points in space, meaning in your reality, in your 3D space. Like, imagine you're allocating points to each point in your space. You can effectively represent that mathematically through a matrix. Like, yeah. And what I mean by that is, like, you can have a row saying this is where this point is. You can have another row saying where this, you can have another one saying where this point is, blah, blah, blah.
And a matrix is almost like, imagine Connect
combination
4.
Of all of them. Yeah.
Yeah, it's like, it looks like Connect 4 with numbers instead of chips.
Right. Locating wherever you want to, what information you're trying to get in map, whatever. That's like the basic rundown of it. It's a little bit, but that's kind of what a Hilbert space is. It just says that you have an infinite number of these that you can that you can fit information in. And there are certain rules allowed, blah, blah, blah.
Right. But barring all the details, it's just basically, imagine a time, like we have the 3 dimensions of space, you know, up, down, left, right, side, or whatever. And then we always say like end time as dimension. Yeah. But imagine if there were 2 dimensions of time. What does that even look like? How does that make any sense?
Yeah.
You know, so this is where it could be. This is why I'm a little bit hesitant on the Penrose thing that you're saying. I don't even know exactly the details of it, but I imagine that this Everettian approach is different than the normal conception of what we think of as spatial dimensions.
Yeah.
So
probably. Yeah, you're probably right. That's kind of the issue. There's a meme of Carl Sagan out there.
Yeah.
Where he says, that's a nice theory. It'd be a shame if someone tested it. and yeah, that's kind of where a lot of physicists now, physics is nowadays, where you have these concepts that are trying to reconcile with quantum mechanics, because we still haven't married quantum mechanics and relativity.
Right.
And a lot of people think...
Well, I thought they did quantum mechanics with relativity. With special relativity. But we need general relativity.
We need general relativity, okay. Yeah. Or gravity, some people want to say. So it's... And some people's inclinations are just... Because quantum mechanics is so kooky, some people's inclination is to go to quantum mechanics. But a lot of people are like, no, it's well tested. In fact, Bell's experiment, this you can look at... you can Google Bell's inequality if you want to learn more about this, but
we also talked about it a little bit in one of our videos.
Did. And it's all the fucking, I'm sorry to cuss, but all the fingers are pointing to general relativity being something. There's something wrong with that, not necessarily quantum mechanics. Yeah,
enlighten me on that, because I think with what we've found so far is like Einstein's been right on everything in general relativity. All his things have been having multiple experiments and confirmation over the past, even like the past few couple of years, you know.
He has, but the thing is, like, we're kind of at a standstill because all experiments of quantum mechanics are showing us that no, this is indeed, like, the universe is non-local, sort of like effectively saying, well, GR, we don't have the whole picture with GR.
How do we not, though? Just because we have the infinities when it comes to the equations,
I think,
like in a black hole and whatnot.
I mean, that may be a part of it, but also because entanglement is such a unique property in quantum mechanics that effectively shits on general relativity because it violates causality for some.
It doesn't, though.
Like in certain, it doesn't. I think. I think certain not interpretations, but certain Duncan experiments or mind, what would you say?
Thought experiments?
Thought experiments, yeah. They actually say, well, no, because information isn't...
you can clearly see that you cannot transfer information faster than the speed of light. So it doesn't violate anything in relativity. At
least in signal, there's no signal being transmitted.
Yeah.
But effectively, there is still some preservation of information there that's happening.
There isn't.
You will never know. I mean, you would know. You wouldn't know, but there is a certain connection there between two that are
There's a connection.
Two spatially distant objects are still how do you say?
Connected?
Yeah.
But that does not violate relativity because it's like you were saying earlier, it has to violate causality.
Yeah.
And the thing is, relativity is formulated in such a way where you're not violating causality.
Yeah.
That does not violate causality because there is no information that you can gain from entangled systems.
Very true. I agree.
It doesn't have any clash there.
I agree, but I think maybe it's like the fact that GR makes, maybe it doesn't need to say anything about the entanglement thing. But
yeah, I think the issue is just the fact that for some reason the math just doesn't work because I think the root is gravity because we still don't really know what the hell is going on with gravity.
Yeah.
Just because, I don't think we understand how gravity works that well. So I think that's where the main breakdown is.
Yeah, but people are going to, but this is what I'm trying to say. I guess just to bring it back. Quantum mechanics, people are pointing the finger at quantum mechanics, just being like, we still don't understand this. And I think it makes sense to look at quantum mechanics and be like, okay, we need to really understand philosophically what's going on here. Yeah, like there is, we know how to use it, but it's the analog that people say, like, most people don't know how a car works.
Right.
But we still know how to use it. We get by like using it, but
right.
And that's how we do with quantum mechanics. And it's
we need to start taking a more Einsteinian approach. And you know what the interesting thing is when Einstein was alive during quantum mechanics, he was the reason why all these big, experiments and holes were being had a light shown on them in the first place.
Yeah.
So maybe if we return to that approach, we could have more of these spotlights on these weird issues.
So you're saying if we had more skeptics, like, oh, okay, but that's the issue. You can't be a skeptic and be a nobody.
Yeah, it's true.
You gotta.
You can if you have a worthwhile skepticism that makes sense to the wider audience that's analyzing it at that level.
But you'd have to be a public figure.
No, you don't. Because imagine this: if you just wrote a paper on some particular aspect about quantum mechanics, and it was written in the language of physicists, and you gave it to the right people, I mean, it's clear as day if it makes sense.
Yes. Okay, yeah. But there is some politics, though. Like Sean was saying, he ran into issues in his department because he wanted to investigate this. And he had to go over to the philosophy department just to talk about some of the things he wanted to discuss.
Right. Well, I think the politics part is the fact that no one wants to be paying your ass to sit around as like a philosopher. Unless you're in the philosophy department, right? In physics, it's all about results, about research, about getting grants, about funding, all that stuff. So you can't really get funding by twiddling your thumbs thinking about the nature of of quantum mechanics, right? Well, we think about the nature of reality, but even theoretical physicists are trying to do things to devise experiments to prove some part of some theory or something.
Right. Well, the thing is,
let me make sure I didn't move that camera.
I don't think you did, but. The thing is with like physics nowadays, I think is mostly model based. Like we try to model systems or model physical systems as opposed to like really understanding the physical underpinnings of.
Yeah, I think you're right.
Well, we try to say that the math will reveal to us the physics.
Yeah. Yeah, you're right. There's definitely a lot of like model fitting and model building and such.
Yeah.
There's a lot of different.
But then when we're done with the model, when we're done building the model, we're like, this is the physics.
Yeah.
So, but like, when you're in an impasse like we are today, or in our generation, we have to think like Einstein. We have to be skeptical a little bit, kind of probe the foundations of our understanding and basically go back to the drawing board.
I think it's a return. I think a big light is going to be shown when we have more of an Einsteinian approach. I'm thinking. That's what my intuition is kind of saying with things like quantum mechanics.
Yeah.
But we'll see. I mean, always, I think another thing that could happen is just the fact that if we get to some technological limit, that might even help. But it just might be slower.
Because like I was always thinking about like what would happen if Einstein didn't exist? Would we still understand relativity at some level? And then I was thinking, oh yeah, but we would like eventually if we got to a point where we're trying to build GPS.
Yeah.
Like we would have realized that there's a discrepancy between the satellites and then on ground their time signals, and we'd say, what the fuck is happening? And then when you actually start messing around with the equations, you'll see, oh, these are actually at two different times. And then you can think about that. So I think if we push the technology enough, we might get there.
I think
it's just it might be a slower process.
And I think that's what's happening. I think he mentioned this too. Sean mentioned this. He said we're kind of us trying to develop quantum computing.
Yeah.
Has made us question the foundations because we realize, well, there are certain things that we're not allowed to do, and there's certain things that we are allowed to do, and then us probing the quantum world in a way that we're trying to get outcomes from it is testing our limitations of understanding.
Right.
And yeah, I think it's going to be very interesting, especially since I think the quantum mechanics that we've developed so far may not be enough to get quantum computing to where we want it to be.
Yeah. Actually, did you hear recently about Google's announcement?
Yeah.
They announced with Google?
They've achieved quantum supremacy.
Yeah. So that was pretty interesting. I don't think they officially announced it. I think it was a leak.
Yeah.
But yeah, I think NASA had their website and then they took it down or something.
You know what that means?
What?
I'm asking you. Do you know
I do.
What does that mean?
So quantum supremacy is the limit that you reach when you have essentially proven that your quantum computer can outperform a classical computer at some certain task.
Okay.
And thus far, every single thing that we've done with quantum computers has had a classical analog that could be done in just at the same amount of time, or not as good. So this is the first time, apparently, from this leaked document. I haven't seen it. The claim is that this quantum algorithm has performed some task that takes about 200 seconds, whereas a classical computer would take about 10,000 years to solve the problem. So that would be a true instance of quantum supremacy if that's actually a legitimate thing. Except, of course, this is a leak, and I don't think it's been confirmed yet. I think it was leaked by legitimate sources, and I think it was on NASA's website for some time, so it seems real. But we'll have to see what the full story is in the future.
Yeah, it's kind of scary because quantum supremacy means that you can, if your engineers are really good, you can break encryption. If
it can do the Shor's algorithm.
If they're good, if they know how to use the code, if they know how to program well and program well enough already using this quantum.
Well, the programming I don't think is the hard part. I think it's just a matter of building the quantum computer.
You think so?
Yeah, because the quantum computer is the hard part, right? Because you have to have enough coherent states and enough qubits to be able to do some kind of large prime factorization. The easy part has already been the code is everything has already been made. Like Peter Shor has already laid the foundation of how to do this prime factorization. Everything. Yeah. Like that all is solid. The quantum gates and everything are all established.
Yeah.
The hard part is just actually achieving the computer itself.
Oh, I see.
And maintaining that coherence time, which is basically how stable a qubit is going to be in that system.
Yeah. Damn. So we're saying a lot of jargon in this.
Okay. Yeah, I think we might have.
So, but anyway, there's a lot going on in quantum mechanics, and it's it kind of like Sean, appearing on this one made us reflect a lot about, just where quantum mechanics is. We may not have time to maybe
some time.
Maybe we do. Yeah, maybe we do. Well, there's he started talking about interpretations of quantum mechanics.
Yeah,
briefly. And
what do you mean, like many worlds versus Copenhagen?
Many worlds versus Copenhagen, and we kind of got into that a little bit, but there are other competing theories. I think you mentioned GRW.
What is that?
Won't get into the acronym because I don't know how to pronounce their names.
Okay.
But you can Google these if you want to know more. GRW, there's the Bayesian approach.
Okay. There's actually a lot of
interpretations. I was Wikipediaing, and there was like 8 or 9. I was like, damn, I didn't realize. So
yeah, and they're all very, like I said, some of them have problems. Like the most famous one is the Bohmian mechanics interpretation, which are you familiar with it?
I looked at it on Wiki, and actually I wanted to interrupt real quick because I took a poll on Twitter.
Yeah.
Maybe you could pull it up, Juan. I took a poll on Twitter of the quantum of the interpretations that people were interested in, and I got like 5 votes, and one of them on there had like 2 votes, and I was like, oh, actually, I guess people have heard of this interpretation. Maybe we should read it on Wiki just to see what it is. If you could tell me what it is.
So the poll.
Just go to the my tweets.
Yeah. So the poll has many worlds and ensemble interpretation at about pretty much the same. And
what's the percentage?
40%.
Yeah, so ensemble interpretation, I guess, is something that people are like.
Yeah, well, I am kind of familiar with this interpretation.
Are you really?
So
let's read it.
If I remember correctly, the ensemble interpretation has the...
I have it right here.
It's like an interaction between like the macro system and the micro system. If I remember correctly, it's... Or maybe I'm mixing 2 theories together. Go ahead.
Let me
I just want
it.
to make sure that it's the right one.
So it says the ensemble interpretation of quantum mechanics considers the quantum state description to apply only to an ensemble similarly prepared systems. An ensemble of similarly prepared systems, rather than supposing that it exhaustively represents an individual physical system. The advocates of the ensemble interpretation of quantum mechanics claim that it is minimalist, making the fewest physical assumptions about the meaning of the standard mathematical formalism. It proposes to take to the fullest extent the statistical interpretation of Max Born, for which he won his Nobel Prize in Physics. For example, a new version of the ensemble interpretation that relies on a new formulation of probability theory was introduced by Ray Shaya, blah, blah, blah.
Yeah. I
didn't really get much from that. Did you understand?
I think, yeah, I wrote an essay back in the day about competing interpretations. This was like maybe 4 years ago now, but
yeah.
And I think if I remember correctly, and if you're in the comment section and you know, if I'm wrong about this, because I think the ensemble interpretation is sort of the same as the decoherence interpretation. I think. And what I mean by that is von Neumann actually had an approach mathematically. And I think we kind of use this approach somewhat, I think, in statistical mechanics. Correct me if I'm wrong. But
there was some approach that I saw that had something to do with statistical mechanics.
Yeah, so because you have to think about the system as you, the measure, you're an ensemble of particles. You're a huge system of particles. And yeah, you have some emergent amount of, like, you have emerging physics, right? Where it's like molecules coming together that they create their own emerging physics.
But that becomes you're saying the ensemble creates a classical system. Is that what you're saying, or no?
Yes. Okay. And there might be a critical point.
Yeah.
Where that becomes, like, it crosses a threshold between quantum and classical, right?
Right.
That's undefined to me. But as far as von Neumann's assumptions that I think were made, were that you look at the system as, like, say, sort of like a, how would you say? If you look at images of a scanning tunneling microscope, an STM, it has like a pyramidal tip, and at the tip you have like one atom of something, typically, like ideally, right? And it scans over the surface of another material, right? And but that's sort of the image that von Neumann had, I think, drawn mathematically in his head. He was trying to see the system, how it interacts. And he's saying, like, how does this large classical thing interact with an atomic, a quantum system, so to say.
So the quantum system being the tip of the tunneling microscope, and then the classical system being the giant material that it's scanning over?
I would say yes. And in the instance where, but let's remove all the other atoms. We're looking at one.
Okay.
If we're looking at one atom with one electron, let's say the hydrogen, to be simple, and you have this large microscope and it interacts with that one atomic system.
Okay.
What happens? Like he was asking himself that, like, what happens, right?
Okay.
Like, so you have to draw the mathematics for that, and like you know.
But how is that different, or what is that? What's the big picture behind that?
So his thing that people started developing on was based off of decoherence, meaning like this interaction, the quantum system was in a coherent state, or the electron, I guess, in this picture was in a coherent state. Meaning it was undisturbed.
Mm-hmm.
And once it becomes disturbed, it collapses.
Yeah.
So sort of you ruin the equilibrium in the system because you're a big system of particles and you're ruining the potential in a sense. Like now if you look at the Hamiltonian, this is physics talk, but
Hamiltonian just means the total energy.
The total energy, right? So your total energy, now you're introducing energy from you coming into the vicinity of this this electron. So this electron starts to feel you. So you ruin its perfect
coherence.
Equilibrium. Yeah. So that's kind of the picture that he.
Okay, so this one has a focus on coherence.
Yeah.
Which probably was because of quantum computing, I would imagine, because that's one of the biggest factors of quantum computers.
I think people started if this is the correct interpretation of the ensemble one. I think people started approaching that interpretation much more seriously because of this, because the picture,
because it has that practical application.
Yeah,
to it.
and it makes a lot more sense, right?
Okay.
Like you kind of have some intuition once you learn the quantum mechanics and how we use energy as a picture of interaction and stuff like that.
Right. Interesting.
Yeah.
We'll have to read up some more on the different interpretations, maybe even make a whole video on it.
Yeah, I mean, that one deserves its own video.
Yeah.
It really does.
Because there's a lot more than I expected.
Oh, hell yeah.
I was like, damn.
Some of them are kind of brushed off.
Yeah.
There are some that are
I think the one that you were just mentioning, the Bohmian.
The Bohmian one.
Yeah.
Yeah, Bohmian mechanics is another favorite. That was a favorite for a while. That one deserves some video too.
But you're saying it got brushed off or no?
Yeah.
Okay, yeah. I thought so.
Yeah. I mean, it just mainly comes down to like us not being able to work the math out.
So it's just too complicated.
We, like you were saying, we don't like things that are divergent.
Yeah.
So we got a lot of
we're like,
infinities.
fuck that.
Yeah. You couldn't do what's called renormalization in the picture, and it just didn't translate to a lot of the new ideas that we're developing.
I see.
So we kind of trashed it.
Okay.
But it was cool. It gave you a lot of the same results. And in fact, there was some physicists from, I think, MIT or some really great school like Max Planck Institute that kind of tried to draw like a classical analog. Like they tried to build a Bohmian system. And they have since been ruled out, actually. So I think people were saying that they were using junk science. And
Okay.
So yeah, that one's kind of been effectively thrown out the window.
I see.
For now, I don't know. Might change once somebody comes and develops something more. But
I actually got a question for you, Juan.
Yeah.
So, do you think that multiple interpretations of the same system is useful, or do you think we should always try to strive for one single interpretation of something?
There shouldn't be room for interpretation. I think this is what, if you, there's another episode with our friend Joe that we did, and his main critique was of modern quantum mechanics is that it shouldn't be open to interpretation. He said there should be one, and I'm inclined to agree.
But now my question is more along the lines of, do you think we should develop multiple interpretations while it's still unknown, or do you think we should strive for a singular one? And if that one doesn't pan out, scrap it, then develop another one.
Well, the thing is, we have conversion to one, but that's a Copenhagen one, right? Like
it's still up for debate, though. Kind of, it's like it hasn't converged really yet.
I think effectively it's converged to that because it's useful, but in terms of a physical underpinning of a lot of like the the real bigger metaphysical questions.
Mm-hmm.
That's why people go to like the other interpretations. I think it's useful to have more than one interpretation, especially if you're just preoccupied with the engineering aspect of it. Like, I'm getting the results I want from this particular setup.
Yeah.
Then I think it's useful to have more than one interpretation for sure.
Mm-hmm.
Yeah. What about you? What do you think?
I think ultimately it's useful to try to come up with as many interpretations as possible.
Yeah.
Because what I think is it will eventually lead to a singular interpretation. And what gives me kind of hope for that is we've seen it already with string theory. If you remember back in the days with string theory, there were like seven different ways to interpret string theory.
Yeah.
And people were all like, what the fuck is going on? Why are there 7 different ways? And it was kind of like they were looking, the description of this, I think I heard from Michio Kaku, was you're looking at the tail, one person's looking at the ears, the other one's looking at the feet. And it's kind of like, oh, the big picture is actually the elephant.
Yeah.
So that's when Edward Witten came along and he strung them all together. To make the overall arching M theory.
Yeah.
And then that kind of made it so, everybody had a different interpretation of it, but they all kind of converged into one thing. So I think you should be looking for as many different interpretations as you can to something, and then I would hope that from all of those angles, you'll eventually get a piece of the puzzle that's really part of the coherency of the entire picture.
I think I agree. Yeah, it's you definitely do. We need that. Yeah, we need that because we need as much information. I actually had an idea the other day.
Oh, what you got?
So I was like, man, okay. I was feeling kind of creative. I was watching this experiment that we set up, and you've probably seen this experiment in like classic physics labs. But you have a strobe light, and you match the frequency of a fan blade. That's
one of my favorites.
It's cool. It's
trippy.
A cool experiment. You could probably do this yourself at home. Color one of your fan blades and like have a strobe light or something that measures the frequency. And what I mean by frequency is the frequency.
Well, just how many times it spins per second.
That, but how many times the light turns on and off.
Okay.
The frequency of the light. So the frequency of how fast the light is switching on and off. So, so in this experiment, we asked the students to try to match the frequency from the strobe light to the fan, right? If you match the frequencies, what you should see is the fan blade standing still. Because if you're matching it, it looks stationary. Yeah. So standing thing. Now the reality of it is that it's still spinning, but it looks like it's standing still. Yeah.
This is why your camera phone has those weird trippy effects when you have moving or objects with some kind of frequency. Like if your camera matches up with the same frame rates, then it looks like you can see like a helicopter just frozen. Its blades just are frozen in air.
Exactly. Yeah. Yeah. You can look up YouTube videos about this, right? Yeah. And that's pretty much what I was thinking. Like, well, that's kind of funny. Like, I wonder if there's a sort of quantum analog, right? Like in quantum mechanics, we treat things in an interesting way. Okay. Let's just say it that way, right? I'm not going to get into too many details, but let's say this is mainly for the physicists out here, but okay. But let's say you're dealing with a quantum system, right? And let's say that you're trying to probe, let's say, a hydrogen atom with one electron or something, and the electron's in the unperturbed S state. I mean, S equals 0 state, right? Where like possible values are 1/2 plus minus 1/2.
Okay, so its spin is 0.
Yeah, totally. Okay, right. So there's one electron kind of around. Its wave function is sort of around the atom somewhere. The wave function says that it's
in space. It's
in space around the atom somewhere. Yeah. Now, I was kind of thinking, it'd be interesting to see if, because there are inherent probabilities built in to quantum mechanics. Now, we say probabilities, but really they're deterministic probabilities, meaning there are a certain set of values that we know that can be obtained. You know what I'm saying?
Yes.
They're only a set of values. It's not like you can get any random number that you pull out of your ass.
Like, it's like it has to be in the state, the overall state of the system.
Yeah, so they're so pretty much a set of values, like a sort of deck of cards, and you only have a certain number of cards that you know already.
Yeah.
So so I was thinking, well, part of quantum mechanics is like you won't I don't think you can, at least the formalism says, I don't think you can say with 100% definitively say, I'm always going to get this energy value. I'm always going to get this eigenvalue, as they like to say. If I measure that hydrogen atom,
okay,
I'm going to get a certain probabilities.
You are.
So, yeah. That's what modern quantum mechanics is, right? But thinking about this fan thing, I was like, oh, that'd be cool if what if you match the frequency of whatever because in the strobe light experiment, you're matching the natural frequency of the fan so that it looks stationary.
Okay.
So it's like, it's like, what if we can sort of do that in a quantum system is what I was trying to say.
But
like
how
if you can match the natural frequency of the, like, meaning like if I wrote out energy, by the way, I'm not trying to use frequency in some like hokey fucking way.
Okay.
I'm saying like, the energy as defined by h bar omega. Mm-hmm. Right. We see that thrown in there a lot of the time.
So omega would be the frequency.
Yeah.
Okay.
So if let's say you know the frequency of your system.
Yeah.
The natural frequency of the system. Let's say you load up a laser and you shoot it at your atom.
Okay.
Is that? I don't think I already was like thinking about it and I was like, I don't think it's possible, but I think it's a cool idea. Like,
so h bar omega is kind of the quantized energy.
Yeah.
Of, let's say, of some, I forget which system it goes with. Which one does h bar omega go with?
Any sort of massless.
Okay, so like a photon, for example.
Yeah.
Okay, and you can have different integer values of h bar omega.
Sure.
And that omega corresponds to the wavelength of the photon.
Yeah, if you wanted, let's say I wanted to shine a photon or send a photon to this system.
But then you're interrupting that system. You're collapsing it.
I am. But I'm wondering if I could always get the same eigenvalue if I match the natural frequency, But it may not be. I think
I have to really think about that because quantum mechanics already doesn't make enough sense to me. So now I'd have to really think. And this is another thing I've noticed with me that I wish I had better knowledge of. Although I've taken quantum mechanics for 3 semesters, I feel like I still don't really get it because the only way you really start to understand things is when you do the experiments and you can see them in real life. Mm-hmm. I still don't get a lot of like how they do certain quantum experiments. For instance, like in the future, we want to do a video on quantum information.
Yeah.
Like I still don't understand how you put an object in superposition. I don't get how you would put a particle in a superposition.
I think they do it. I think maybe we've mentioned this, but
I also don't get the Stern-Gerlach. Sean Carroll talked about the spin up. It goes through the electromagnets and then it spin up. Yeah. It either goes up or down, and then they turn it sideways and it goes either up or down. I still don't really get that Stern-Gerlach either.
Maybe I can sort of give an explanation because it stumped me too.
Yeah,
but I tried to spend a lot of time with this because
but how's it always spin up and down? Like that's why I don't understand.
That's the superposition.
But why wouldn't it go sideways sometimes? Because then it seems like it's spatial somehow. If it always goes up and down, like why? It seems like you should at least have left or right. Then
I think what the experiment is trying to show is that there's something funky with this because classically you're filtering things out.
Yeah.
Or you should be filtering things out, but it's not.
Yeah, but I just don't get why it's always up or down. Like, why can't it be left or right sometimes? Let's say if you only have one electromagnet, why can't it be left or right?
What do you mean?
So so let's say this. You have a particle that goes through an electromagnet.
Let's say it's an electron.
Yeah, an electron.
But that's what I mean by that's what they mean by
it goes up
and down
or down.
Yeah,
because of spin up or spin down.
Yeah.
But why can't it be left or right? Why is it always up and down?
I think because the polarization of the, like, you know what I mean? It needs to either go, like, you know, if it's positive field, it'll probably go this way.
Okay, so if I turned it like sideways, you think it'd go left or right?
Yeah. But
it's just so weird still, because then even it's like, because you're saying okay, you're saying that when the electron enters in, it somehow becomes polarized to up or down?
Yeah. Because that's what they're trying to do. They're trying to filter it out, but then when they put it through another filter, they see, dude, this thing still has the fucking spin down. Sorry, Cuss, but
okay.
But that's the nature of, they're saying, that's the nature of superposition. Like, for some reason, it goes, like, in between here and here, there's still something going on where, like, the states are preserved.
Yeah.
Like, we never lose that for some reason. It's strange. It is strange, right?
Yeah.
But that's kind of like
I think I understand now that we just said it.
Yeah. No, it's fucked.
Yeah, quantum mechanics is so strange.
It's really strange, man. It's funky. There's a lot of like, even till today, like, I have stacks of books, but because like if you look back there's what is it? Understanding More Quantum Mechanics. Right behind you, there's a book called Understanding More Quantum Mechanics.
Okay.
It's a really good book, but like, it's something that I didn't learn to appreciate until after. Like, a lot of the time when you finish up your core classes, right? Mm-hmm. You can finally breathe.
Yeah.
You know what I'm saying?
Yeah.
Like, and
you get the false sense that you understand things.
No, you do, but then I try to go back and clean up any misconceptions, because it's no one actually, and I feel like no one, maybe it's just a lack of good textbooks in my opinion, but there are very few books that, like I was saying, spell it out for you, because then that makes me, sometimes this is my thing that's like makes me lazy, but
fuck that.
There's certain, like, they give you like particle in a box, right?
Yeah.
They give you that, and they never really tell you, oh, this is, in real life, we treat, you know, lattices like this. Like, we treat bound electrons like this. Like, the potential is like a box.
Okay.
We look at a simple model like that. Like, a bound electron is like effectively a particle in a box.
Mm-hmm.
They don't say that for the most part. I think in some condensed matter books, they kind of, but
that's
you have
really
to go into a
to me,
specialized. You have to go into a whole specialized thing to even see that.
Right. That's really annoying to me, though.
It is annoying,
because it's like,
give me the real picture.
The thing is, we're classical beings.
Yeah.
We're Newtonian beings.
Yeah.
Like, I get that you just want to give us the math and shit in an abstract form, but like, I need something real to hold on to, or else it's just going to go out of my mind. I'm just going to say this is some random ass generalization that I have nothing to hold on to.
I can't tie it to my experience.
Yeah. You remember how long it took me to understand what the fuck a harmonic oscillator was in quantum mechanics? And then we finally understood it after we took condensed matter and realized, oh, it's just like a particle within a lattice of other atoms.
Yeah.
So, like, that annoys me.
It is
greatly.
It is super annoying, and it's
just like, it's either like showboating or just like being so far distant that you're just you forget that there is a reality to consider.
Yeah, it's really annoying, and
I also figured out that the ladder operators that Dirac invented are not that complicated either. It's just if you take the Hamiltonian, once again, that's just the expression for energy. If you take the Hamiltonian using a different form of math, where if you take where you factorize it and you just have imaginary components, it actually all comes out very easily to derive.
Yeah.
Like, I'm like, oh, it actually makes sense. I get the ladder operators now.
Yeah, I've seen that proof. I should probably brush up on it.
It's not some random. I was just like, how did he come up with ladder operators? I don't get how he came up with this shit.
Yeah.
But it's really easy. You just take the math, and then the math does everything for you.
Yeah, some things are super powerful and really simple, and like even like commutation rules. There was a frustration there because, like,
the commutator. Like, what does it mean?
Right, and I feel like some professors didn't really, at least in my undergrad, I think I wasn't until graduate school that there was one professor that I can think of that kind of explained it well, but
it's just straight up a mathematical tool.
It is, but you know where I heard it put best?
What?
Was by Eric Weinstein or Weinstein.
Oh, what'd he say?
He was like, commutation rules are basically the order at which you can do things.
Oh yeah,
and he was
you can't
saying,
put your pants on.
Yeah.
Yeah.
And I was like, wow,
that's a great way to say it.
Perfect way to put it.
Yeah, so simple,
elegant, and it's tied to your real experience.
Right.
You know what I'm saying? It's like,
what did he say exactly? Like, if someone put their underwear first before their pants, or if they did,
exactly.
But you don't know if someone put their shirt on before their pants.
Yes.
Yeah.
Thank you. That's exactly what it is. And math follows the same. There's certain operations that, you can know which the order matters.
Right.
In a sense.
Yeah, that's why I love Weinstein. He's just such a good explainer. He explains things in such a really easy, simple way.
I think there needs to be more physicists like that, with that mindset of, because a lot of them just say, if you don't get it, then
you're fucking retarded. Get out of my class.
It's absurd. It really is.
Yeah.
Anyway,
We're
I feel
65 minutes too, by the way.
Yeah, I feel like for the maybe a couple next episodes, I think I bought Sean Carroll's book.
Yeah, go ahead and plug that bad boy.
Something Deeply Hidden.
Pay us, Sean.
We're gonna. Well, I'm definitely gonna read this, and when I'm done, maybe you can take a look at it. But I do want to go more deeper into the interpretations as outlined in here, and then maybe sort of relay that to y'all.
Maybe we can do it if we can get around to doing an episode on the different interpretations of quantum mechanics.
Because this was more of like us reacting. It was just more reacting to like Sean's sort of comments. And,
him being on Joe Rogan and everything. We jump on it.
So yeah. Anyway, stay tuned for that. And thanks for listening. Hello. Thank you. Well, not hello, actually. Thank you just for making it.
Yes.
This far.
You done good, people.
Thank you again.
Keep on supporting. You guys are great.
Yeah, keep on keeping on. Thank you for listening, and make sure to follow us, subscribe, like, all that stuff. Share, especially if wherever you're most active socially, share that. Yeah.
And that's it, guys. Also follow us on Twitter at Eigenbros, and we'll see you next time.
Yes. Peace.
I don't know what that means, to play us out. What does that mean? To end the show? To end the show? To end the show? To end the show?